Oxycodone is available again as the hydrochloride salt in tablets and capsules. I think that we have discussed that, but it was repeated. So again, that is the structural modification of ring C. So I think we have finished the whole of this. So we don't need to go back there. So that is the structural modification of the alicyclic ring, where we have talked about the 14 group, 14 position. We have talked about the 6 position. We have talked about also the 3 positions. So those 3 positions which are part of the alicyclic nature, or alicyclic structure, we have already discussed them. And these are some of the structures that we have just mentioned. Of course, all of us now know morphine. We'll have that group, that group, that group, and that group. That is what we define morphine. Codeine, most important, is that group. Everything else is morphine. Heroin, most important, is that group from there, and this group from there. That is the acetyl group and the acetyl group, because this oxygen is from the hydroxyl group that is found at position number 3. So the acetyl group there and the acetyl group there are the groups that differentiate heroin from morphine. Every other structure is the same. Let us first of all leave morphine, we're going to discuss them. Then you have the hydromorphone. When you look at the hydromorphone, difference there and difference there. That's the only difference. Saturation at that position, oxidation at that position. And of course, it's a morphine. Then when you look at hydrocodone, it's first and foremost, it is a codeine, and then the codeine has been changed to codone because of that there. And all codones also have the saturation at that point. Then we have also oxycodone. So first of all, you look at, is it a morphone, is it a codone? Because the when it's a morphine, it means that position 3 it has a hydroxyl group. If it's a codone, the first thing you put is a methoxy group at position number 3. So these are codones. So that group there, very important to differentiate it from a morphone. And then everything else apart. And then, of course, you see it's an oxy here. It is an oxy here. That oxy means it must have this beta hydroxyl group at position number 14. And then the codones, all of them, as we have seen, must have the saturation at position number 7, 8, and also oxidation of position number 6. So I hope now it's getting a bit clearer. I hope it is, because they are just definite structural features that you differentiate a morphine from a codeine, from a heroin. I mean, there's definite structural features from a hydromorphone, a hydrocodone, and oxycodone. They are very specific, and you must know them because you should be able to draw any of the derivatives of morphine, any of the morphine and its analogs. You can be able to draw any of them as long as you understand what the name means. The names of these drugs can give you the structure. The name of these drugs, when you understand the name is equal to a specific structure. So I've said we leave out the morphinan and the vofano, which is a morphinan. We are going to look at the morphinans a little bit later. Then the other one is the phenyl ring. We have also discussed the phenyl ring. So we are saying the phenyl aromatic ring is important, and the hydroxyl group is also important. Remove or decrease in activity. Any other substitution on the phenyl ring, again, will diminish or will cause the molecule to lose analgesic activity. Then, so I think now we are done with that. This thing here, we are going to do that one. We'll do it as a derivative. We are done with the whole of that section. So now, and we have, of course, now we have looked at the aromatic ring. So now our main area is position number 17. And this again is very general, modification of a tertiary nitrogen. So we are saying that for starters, this requires to be tertiary. And you can see that group there, that group there, that group there. And usually this, because this is usually not a hydrogen. If it's a hydrogen, then it becomes no. And we have seen the no derivatives have much lower activity than the ones that are substituted. I want to keep wetting my throat so it doesn't bring problems. So the no ones are less active than the ones that are saturated. So we are starting with the tertiary amine for good opioid activity, and then we are seeing the size of the nitrogen substitution can dictate the compound's potency and whether it is an agonist or an antagonist. And this, again, this is very general. So I'm just starting with this very general so that we have a rough idea, but we're going to look at each of those points and look at the subsequent. So this group here is very important. As we have already seen, it can be a hydrogen, it can be a methyl group. Most of them have a methyl group. Others have even larger groups and methyl group. And we are saying this will dictate the activity of the agonist in terms of how much analgesic activity does it have. Is it the potency of the agonist? Is it also an agonist? Is it an antagonist? So that is mainly determined by that group there. Again, you see very good examples. We have mentioned the Trexon, we have mentioned the Naloxone, which are actually antagonists by change of this group here. And you see when you look at these substituents, they are similar to some of the other drugs that have agonist activity. The size of the nitrogen substitution can also dictate, or we have done that. The N-methyl substitution is usually very good for agonist property when increased. When the size is increased, when it's increased, the size of the substitution by 3 to 5 carbon. In other words, when we increase the size of the R to about between 3 to 5 carbon, results in antagonistic activity. So when we increase the size to between 3 to 5 carbons, you look at methyl, it's 1 carbon atom. So when we increase the size to 3 to 5 carbon atoms, more often than not, it results into antagonistic activity. But some of the larger substituents on end returns agonistic property of the opioids. For example, we will look at the N-phenyl ethyl derivative. N-phenyl ethyl derivative. We look at N-phenyl ethyl derivative. Phenyl ethyl derivative. I don't know whether this pen of mine can write. It's a better idea. So if we are looking at N-phenyl ethyl derivative, let me just try it. Sorry, task. Don't worry the fact that it's a bit bigger. That's ethyl. And then you have a phenyl group. Nimeanguka sana. So you go that way. Yeah. So we are saying, we have just said that if you increase this group here to between 3 and 5, the compounds become antagonistic. And if you look at now Trexon, Naloxone, that is the position. But if you again increase now to a slightly larger group, like this is what we are calling N-phenyl ethyl. So you can see this is a very large molecule. Somehow, agonist activity comes back. So that is an important point. Remember, I did mention when we are looking at the morphine rules that sometimes you will have exceptions. And this is one exception to that morphine rule, where we said the subsequent R at position 17 is usually a methyl, is usually a small active group for agonist activity. It has been found that phenyl ethyl group can be joined at position number 17 with retention of activity. But when you put most of, you can see this aromatic This group is an aromatic alkyl group. But when you put just alkyl groups or allyl groups is where you have double bonds, then you find the activity of that group changes to be, more often than not, antagonistic activity. Again, as I have said, we are going to look at this one by one. This is just the general introduction. So still larger substituent on N returns agonistic property of the opioids. For example, the N-phenyl ether substitution is 10 times more potent than the N-methyl group. So you can see that there is an exception of the morphine rule, which states that the substituent at position number 17 should be a small group, small alkyl group for activity. I told you, kindly note those exceptions, that it should be a small group for activity, because we are seeing the N-phenyl ethyl substituent derivative of morphine has much higher activity than morphine, actually up to 10 times. N-allele and N-cycloalkyl group leads to narcotic antagonistic activity. N-allele means you have a CH2, a CH2, and then you have a CH, and then a double bond, CH2. Oh God, just touch my throat. That is the allele. So, and if you look at this, this is a group. That is a group that you have in the naloxone. And the minute you put an allele group as in the naloxone, an allele group or a group with a double bond, even in pentazosine, it's a 5-membered group. You put an allele group with a double bond, you introduce antagonistic activity. So that's what we're calling N-allele, like in naloxone. And even if you introduce N-cycloalkyl, cycloalkyl means you have a cyclic ring and a CH2, like cyclopropyl group, cyclopropyl methyl group. And the cyclopropyl methyl group, if you look at the structure of naltrexone, you didn't draw these structures. Naltrexone has a cyclopropyl. It's a cyclopropyl like that. Cyclopropyl, all of us know now. Cyclopropyl is like that. So it has a cyclo. So you're talking the cyclopropyl, that's a cyclopropyl alkyl. So if you look at the structure for naltrexone, which is also a pure antagonist at the mu receptors, it has that. So you're saying if you put an allele group or you put a cycloalkyl group, that leads to narcotic antagonistic property. So I wanted us to understand that, but we are going to look at this structure and be able, one by one, and be able to understand. Again, in general terms, the epoxide bridge, if you remove the 3,4 epoxide bridge in morphine structure, it results in the compounds referred as morphinans. I told you, like the forphanol, I said we'll come back to them. The morphinans, again, that is still a periphery group. Removing that ring, the ring D, so that now the resultant molecule has 4 rings instead of 5 rings, still does not. In fact, it increases the activity with other changes, which you will see. You also do other changes like the oxidation and so on. So that removal of that ring does not diminish activity. The activity is still retained. The morphinans are prepared synthetically as a synthetic procedure yielded compound. Since as the synthetic procedure yielded compound S-less mixture on the liver isomer. Again, just like morphine possesses opioid activity, where the dextro isomer has useful antitussive activity. So again, it's still telling us stereochemistry is too important, that for antitussive activities, the dextro isomer, the dextro methylphan. The dextroisomer is the one which has antitussive activity. The levoisomer is the one which has the analgesic activity, just as for morphine. And of course, we have example of levophanol and butorphanol. And in a minute, we're going to look at the structures. The levophanol is a more potent analgesic, is a stronger, it's a more potent analgesic compound than morphine. So what are we saying? You have lost one ring, but of course, you have done a little bit of structural modification. But the loss of the ring does not have a negative influence on activity. So this morphine is carrying a lot of baggage in terms of the pentacyclic ring. For morphine, remember when you talk about morphine per se, the morphine you require that ring as morphine. That's part of the SAR of morphine. But you can remove the ring to give you other compounds. The compounds that you get are not called morphine. They are called morphinans with increase in analgesic activity. So please remember, if you are discussing a specific drug, you will look at its structure and look at all the important groups. But now when you are saying structural modification of that drug to another, like if you are looking at structural modification of morphine to levophanol, then you will say that that ring can be removed. But when you look at morphine, for morphine, it requires that ring for it to have activity, because you realize if you remove that ring in morphine without other changes, then that drug might not have any good activity. So please always check the question. Is it asking about a specific drug, or is it asking about a class of drugs? So now we are looking at all the structures which we have discussed. So we have that is morphine. It's our general structure. You can have a group there, a different group there, and a different group there. So for morphine, that is a hydrogen, that's a hydrogen, that's a methyl. For ethyl morphine, for ethyl morphine, R is a C2H5 and R prime prime. That I don't think we look at this one. This is a CH3. No, so no, this is a CH3, that's a hydrogen, sorry. So for ethyl morphine, that's a C2H5, that's a CH3, that's a hydrogen. For codeine, that's a methyl group. And of course, here that's our hydrogen, this one is hydrogen, that is not changing, it's still a methyl group. For heroin, we have seen that's a R is an acetyl group, methyl group. For naloxone, again, naloxone is a narcotic analgesic, because you can see this is what we call the allyl group. And we have said when you add an allyl group there, that drug changes activity from agonistic activity to antagonistic activity. So that is one of our first antagonists, naloxone, because as we have discussed, change of that group there to an allyl group will give you antagonist activity. So we're just looking at all the structures just now in a condensed form, the hydromorphine derivatives. So when you have dihydromorphine, remember this 7-8 group has been saturated, and because they are morphine, this will be hydroxyl group. That will be hydroxyl group for them to qualify to be morphine. For it to be a dihydrocodeine, so this would be dihydromorphine and dihydrocodeine derivatives. So for dihydrocodeine, for dihydrocodeine, of course, the only difference is that this R will be a methyl group, everything else will be the same. Only looking at all the structures we'll be looking at in the condensed form. Hydromorphone. So when we look at morphone, we understand this must be a hydroxyl group for it to be, because it's a morphine derivative. This must be a ketone. There must be a saturation at that point there. And this one has to be a hydrogen because it's a morphone. It's not an oxy. So that must be a hydrogen. So hydromorphone, that is a hydroxyl group. R, this one is a hydrogen. R, that one is a methyl group. When you come to oxymorphone, again, that must be a hydroxyl group. Oxymorphone, R cannot, where is our R? This must be a hydroxyl group. I think there's a mistake there. That has to be a hydroxyl group for it to be a morphone. The R prime here must be a hydroxyl group. That must be a hydroxyl group to satisfy an oxy, and of course that must be a methyl group. Hydrocodone, because now the codone, that must be a methoxy group. That here are, because it's a codone, it's not an oxy, that must be a hydrogen, and the final one there must be a methyl. When now we have the oxy, the difference will be at this position here, that must be hydroxyl group. Come on, I'm in class. And I am in class. Is it urgent? I haven't finished class. Is it urgent? So let me finish class. I'm finishing at 11. So when we talk about the codone here, oxy, we are saying here we must have a hydroxyl group. It's a codone, a toxic group, and saturation here, and of course oxidation at that point. So again, this is just for us to be able to compare these different compounds and understand them well. This we have already said, the 14-beta hydroxyl group results in drastic increase in activity in the dihydromorphinone series. So, and that, of course, we have said that beta group there, and of course, the compound change to an oxy, and of course, also 6-methyl. And again, also, it was found also that if the hydroxyl group at position number 6 is changed with a methylene group, incidentally, the resultant compound, which is 6-methylene dihydromorphine. 6-methylene dihydromorphine, because you can see it's not a known. 6-methylene dihydromorphine was found incidentally very active. It was 80, it had 80 times the activity of morphine. So it was found, again, we can understand because the methyl group will increase the lipid solubility of this molecule very, very drastically, and hence increase the activity. So this is an important compound to note because it was found to have extensive, a great increase in activity compared to the other morphine derivatives. Finally, we look at the modification of the nitrogen substituent. Again, we have mentioned it, and we are saying methyl is the optimal substituent for agonist activity, and ethyl also can be used. Ethyl is possible because we have said 3 to 5. So methyl, ethyl, that is okay. That is to give you activity. If you increase between 3 and 5, remember say 3 to 5 will give you an antagonistic activity. If the nitrogen substituent is a hydrogen, analgesic effect is reduced. And of course, addiction ability is also lowered, as we've already discussed. And these are the no derivatives. Again, when you remove the methyl group, you decrease lipid solubility, and therefore you decrease activity. Addition of a phenyl, ethyl substituent in place of methyl results in a 14-fold increase in activity of a morphine. That one we've already said. Quaternary ammonium derivatives, that's why I like looking at this because there might be some 1 or 2 points I've left behind. So quaternary ammonium derivatives such as N-dimethyl morphine have no analgesic activity but do have significant curare-like activity. In other words, if the terminal nitrogen, which is at position number 17, carries a positive charge, do not bind the morphine receptors. But do remember, we do have in the brain, see, we still a little bit to penetrate the BBI, get into the brain, and we do have many other receptors which require a quaternary ammonium ion. And one of that is the curare-like, the curare receptors, and therefore that can bring you a lot of toxicity but no activity. And when you look at other drugs, quite a number of those drugs that bind those other receptors, they do undergo protonation at that position with retention of activity. The nitrogen substituent is a bulky alkyl group such as propyl, isobutyl, or especially aryl. Remember we say bulky alkyl groups. Remember we did say that bulky alkyl group, and also cyclic group or cycloalkyl groups, isobutyl or especially aryl, and cyclopropyl methyl groups the compound becomes a narcotic antagonist. And we do have examples whereby we have already said, if you have looked at cyclopropyl methyl group, the cyclopropyl methyl group is now naltrexone, and the allyl group is now naloxone, and those two drugs are actually narcotic antagonists. Even when you have the isobutyl, like we would find, it's not the one. Sometimes you can even have cyclobutyl methyl group, like butorphanol. Again, they do have antagonistic activity. So these are the features of the nitrogen. Again, very important, because we have said they determine the potency and they determine also the type of activity, whether the potency or whether that molecule is going to be an antagonist or it's going to be an agonist. So they determine not only the potency, but also the type of activity that we are going to have there. Then I think this is the final one of the changes before now we got the morphinans. Yeah. It was also found that you can do what we call annihilation. Annihilation is where now you add another ring. And it was found that if you do annihilation on ring C, you actually increase activity. So and the resultant compounds are what we call the bainas. That's where I am now. Yes. So annihilation, adding a sixth. Remember, we had 5. So that's why I'm putting it here, because we are still doing structural modification of the morphine. We are not removing the rings. We are just adding an extra ring. So adding a 6th ring across carbon 6 and 14 of the C ring of morphine yields what we call the bane compound, such as etophine. Etophine is found to be so potent that it is said to be about 1,000 times as potent as morphine, and you cannot use it even in humans. You cannot use it in a human. You kill them. It is actually used in large animals like elephants. When you want to drive them to sleep, you see them shooting them in the parks when they want to transport them. This is one of the drugs they can use because it has very high analgesic activity. Of course, it also has it also causes the animal to sleep. So it uses the bane compounds such as etophine, which are extremely potent analgesics. These compounds are typically used to immobilize large animals like elephants. So you cannot use them on humans. You will kill them. Replacement of the N-methyl group of the thebanes. So now we are going to look at that structure in a minute. We can look at it. So we are saying, when we look at etophine, when you look at etophine, this is position 1, position 2, position 3, 4, 5, 6. So this is position 6, 7, 8. Then we jump, that is 9, 10, 11, 12, 13, 14. So you can say, we say position 6 and 14. So I hope that you have noted that is correct. So we are doing an annihilation of bringing in a new ring between position 6 and 14. This is ring C. A, B, the whole of this is ring C, and this is ring D, and then ring E. So we have not done any removal of any ring. We have added a ring, and that's what we are calling an annihilation. So I wanted us to note that. Of course, they have done also some other structural changes to get the compound we are calling etophine. But the main change is what we are saying, replacement of the N-methyl group of the thebanes with a methyl cyclopropyl group. Again, remember, at the nitrogen of etophine, you can see you have an N-methyl. So we are saying you replace it with a methyl cyclopropyl group, then you get a drug called buprenorphine. They are buprenorphine, and this is one of the drugs which is actually a partial agonist. So we are saying, therefore, so replacement of the N-methyl group of the banes with a methyl cyclopropyl, like the one that we have in our naltrexone. So we are not changing anything. We're just playing around with the same groups. like the one we have in our Trexon group, yields compounds with mixed agonist, antagonist, or partial. So you can get drugs either with mixed agonist, antagonist, or partial agonist. For example, buprenorphine. A partial opiate, buprenorphine, which is a partial agonist, and partial agonists never produce the maximum activity that is expected. So they do not have 100% efficacy. A partial opiate agonist at mu receptors and an antagonist. So it's a partial, so it has both activities. It's a partial agonist at mu receptors and an antagonist at K1 receptors. As an agonist, it is 25 to 50 times more potent still than morphine, although it is a partial agonist at that. It still does not excite them to the full. It's a partial agonist and it's slightly longer acting. So it can have partial agonist activity at the mu receptors and it has antagonist activity at the K receptors. It is available for IM and sublingual administration and has a much longer half-life. The metabolic pathways for buprenorphine are really not known. If the respiratory depressant activity reaches a ceiling, in other words, the respiratory activity is really not dose dependent. For most of the other narcotic analgesics, the respiratory activity is dose dependent. So the more you increase your dose, the more you increase the toxicity, including respiratory activity, until you get a knockout. But we are saying for buprenorphine, it reaches a maximum. I think this is why we are calling it a partial agonist at the mu, because of I believe of its partial agonist activity at the mu receptor. Its respiratory activity reaches a ceiling, so even if you increase the dose, you do not increase the respiratory depressant activity. It has moderate abuse potential, because I believe also of its antagonist activity, because of its high affinity and slow dissociation from opiate receptors. Larger doses of antagonists, such as naloxone, are required to produce reversal. So if somebody has used it as a drug of abuse, then it has a longer duration of activity. So therefore, you will have to use higher doses, and of course of the pure antagonists like naloxone to reverse its negative effects, its let's say spiritual depressant activity, of course also to reverse the other activities of this drug. So that is a drug. Those two etophine, I hope I don't know whether I will look for the structure of buprenorphine. I think I don't have it today. I will have it next time. Those two are the two examples of another class of drugs whereby there's annihilation, whereby the morphine can be 5 rings. You can increase it to 6 rings. You can reduce it, as you will see, to only 2 rings, and the drug will still have activity. So it is a molecule which is highly flexible to structural modification with retention of activity. So you can see here, as we have said, there we have our methyl group. Here, in this ring here, that ring, ring C is where we are having our annihilation. You can see this gives this ring and that ring. And each of those rings, if you look at them properly, each of those rings has, if you start here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So each of them has 6 carbon atoms. Of course, they have this as the bridge. The whole of this, that carbon and that carbon is a bridge. This carbon and that carbon is a bridge. The bridge, remember, is the common carbons that are shared between the two bicyclic rings. So this is what is shared here. But you can see these are 6 carbon atom ring. That's a 6 carbon atom ring. And therefore, if you now count the rings, that will be A, B, then this now will be C. Let's say that we call that C, and then we still call that our D, and we call that our E.
Excuse me, Dr. Jocelyn.
Yes?
We can't see as you're indicating.
Okay, sorry, let me go back again then. So I'm saying, if you look at this structure, all I'm saying is it will have 6 rings. So we can say that is our first ring, A, which do not change. This here, the whole of this, don't and ignore this line which is here. So I'm talking about the whole of this ring here. That one there, which was our ring B. Will B, still our ring B. So let me remove that. So that will be a ring B, not changing. I hope you can see that. Then we are saying, let us now call this ring here. You can see this dividing line here. Dividing line here. That makes this a bicyclic, this a ring, and that a ring. So we are saying that we call that our A, we call that our A, we call that our B, we call this our C, we call that our D. We don't want to change the status quo. We want to still number them almost the same. We call that our E, and definitely we will have an F. Is it clear now? So we are saying, therefore, we have 1, 2, 3, 4, 5, 6 rings. And that's what we are calling annulation. And again, what I've tried to explain is that when you have this here, that one there, that atom, and this atom here, this atom and that atom is a common atom, and that's what we are calling the bridge. This is a bridge. This is a common atom, and that's a common atom in that ring and that ring. So this is a common atom, that carbon and that carbon is shared by both rings. And that, so when we consider this ring, we are considering this carbon and that carbon. When we are considering this ring, we are also considering that carbon and that carbon. So when we are considering this ring, we say it has 1 side, 2 sides, 3 sides, 4 sides, 5 sides, 6 sides. So it's a cyclohexane. And the same case applies to the other one. So they are both cyclohexane rings. But of course, it's a bicyclic ring. And when we talk about a bicyclic ring will be that ring that has a bridge and has common atoms. So that's what you're saying about this compound. The third bends, there's annulation. And annulation is whereby we have an added extra ring. And the morphine now does not have 5 rings, it has 6. But if you look at the terminal nitrogen, it still, as we can see here, this is our terminal nitrogen, it still has our methyl group there. I hope that's very clear. But when we look at, again, we count position 1, position 2, position 3, position 4, position 4, position 4, position 5, position 6, position 7, so this is position 7, this is our position 6, position 6, position 7, so position 7, position 8, we change anything, position 1, 2, 3, 4, that's again 5, that's our 6, that's our 7, that is our 8, that is our 9, change anything. Yes, that's our position 9, just like the other morphine, and that is where the preparing ring comes from. 9, position 10, position 11, position 11, position 11, position like we have added 12, let's see, 12, 13, no, there's one I've counted, which I shouldn't have counted. This is our position 9. So position 1, 2, 3, 4, 5, 6, 7, 8. That's the one I shouldn't have counted. Let's see, just a minute. That's up. I counted position 14, sorry. Position, so you have to be careful. Position 1, 2, 3. I think the mind is getting tired. 1, 2, 3, 4, 5, 6, 7, 8. Because it should be the same, 8. And then from 8, we go to position 9. Always know position 9 is where the terminal nitrogen comes from. So anytime I make a mistake in numbering them, I know by the fact that then this should always be position 9. This one here. This terminal nitrogen comes from. So position 7, 8, then this would be 9, that would be 10, that would be 11. So 9, 10, 11, 12, right? 12, and then our position 13, very critical. It is a quaternary carbon, and then of course our position 14, and our position 15. So you go back to the side, 15, 16, and 17. So what I wanted us to see is that, but it was good for us to just look at it and be able to number it, is that in these the banes, there is also a slight difference in that if you look at position number 7, there is a substituent, and if you look at their position number 6 in etophine, there is a methoxy group. And we did mention, if you put a methoxy group at position number 6, you increase the analgesic activity. Why? Because you have masked this hydroxyl group, you have increased the lipid solubility. Remember, we did mention the hydroxyl group is not really necessary for activity. When you mask it, you increase lipid solubility. In increasing lipid solubility, you increase the ability of that molecule to penetrate the BBB. Look, and of course, look, that group there is a hydroxyl group. That is what we require for activity, a free hydroxyl group that has not been interfered with. Again, look at our substituent at position number 7. Yes, a very small hydroxyl group compared to the whole of this group here. You look at the whole of this group here, a methyl group from here, the whole of this group. Look at the whole of this group here. The whole of that group is hydrocarbon. It's an alkyl group, it's a hydrocarbon, it's a branch hydrocarbon, very high lipid solubility. But they do put a small hydroxyl group because you cannot, again, compromise 100% on water solubility. That drug will not go into solution. So they put a hydroxyl group to maintain some degree of water solubility. But when you look at this structure, for sure you can see it has much, much higher lipid solubility compared to the other compounds. It has its hydroxyl group at position number 6 masked with a methyl group, again to increase lipid solubility. It has all the other necessary things because you can't see position 7, this position 6, position 7, 8. There is saturation, so there is saturation of the double bond. There is masking of the hydroxyl group at position number 6. There is addition of a highly lipid soluble group at position number 7. The hydroxyl group at position number 3 has been maintained. And of course, there is also an addition of another ring, increasing its lipid solubility, giving those derivatives, the bane derivatives, very high lipid solubility, but maintaining their water solubility by addition of hydroxyl group and a substituent at position number 7. Of course, the terminal nitrogen is there, the ether linkage is there, the hydroxyl group at position number 3 is there, and therefore that molecule has extremely high lipid solubility, penetrates the BBB very rapidly to give you very good analgesic activity. But we have said it can only be used as a tranquilizer for animals. It cannot be used for human beings. It's about 1,000 times, I think. 1,000 times, I think somewhere I read. It's 1,000 times as potent as morphine, and arguably is too potent to be used for human therapy to kill the human being. So in conclusion, we are asking, the morphine analogs, are the morphine analogs any better than morphine? Are the morphine analogs, in terms of analgesic activity, are the morphine analogs any better than morphine? And indeed, of course, if you do a summary, or in fact, that's what we should close with, when you have looked. I think that's what we should close with, because I've not asked you even the slightest question today. So that's what we close with as I check your attendance. What would you say if you were to compare the morphine analogs and morphine in terms of analgesic activity? What would you say? How would you compare the analogs and morphine? Which is better in terms of analgesic activity. Of course, not in terms of toxicity, but when you talk about in terms of analgesic activity, is it morphine or the analogs, which indeed will be the better drug in terms of analgesic activity? Of course, the morphine analogs, the morphine derivatives are drugs that are important, especially if you're talking about palliative care in terminally ill cancer patients, where you just want to give them quality of life. And at least the pain, because pain is very destructive. So at least you want them not to be in excessive pain. So would you be able to account or state, is it the morphine or morphine analogs in terms of analgesic activity? And for whichever you choose, what are your reasons? Can you do that very quickly as we close? Just closing. But I'm not talking anymore. The question is on your side. Is it morphine or it's analogs? As I note, I want to note, as you answer that question, and you say you are present, as you answer the question, and of course also say you are present, I want to note the attendance. Is it morphine or it's analog? Which is better? Oh God, analgesic activity. Thank you, God. I've managed to finish the class. So I'm waiting for your answers, class. Is it morphine or it's analog? It's analogs for analgesic activity. Gem. Tie. I hope you're giving me some answers, are you? I'm trying to note who's present and who's not present as I wait for your answers. Are you there? Sometimes you keep quiet. Kwa nini mmekimya hivyo? Mjibu swali. Which is better, morphine or its analogs? We're not talking about toxicity, but in terms of analgesic activity, which is a better drug, morphine or its analog, and why? In terms of analgesic activity. Brenda, I want just to be, meanwhile, kindly answer as I trying to write your names. Evans Marrow. And I have 35 today, so please don't sign out. Because if you sign out, I will say you are not there. It's going to take me a short time. Consent. So good. Go. One ape. Also getting used to your names. It's Joseph, Camelo, Nano, Esterina, Maniana, Amek Abenga, Owen teach. Owen teach. Ed James, Muendi, James Kani, Kimani Ann. Muhende, I think you've signed off. Diana Abiso. Lady James Muinde. Rao Mafwali. Naomi Sipatoi. Demo Patricia Nyala McKenna. Olwanda Christine Omeni Oluch Shalina. Na wale wana signing sahi. Please don't sign in now, because you are messing everything. Shalina, Kadeen, Sharon, Mbua, Sylvia Irongo, then Simon Waigo, Stella Joki, Tonui. I'll get it right, I'll be liar. And then Wendy Odwall. It goes alphabetically. Wendy Odwall. So I have 35 of you. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 23, 24, 25, 27, 28, 29. I have missed out some. Please let me call out your name very quickly and chat me up if you don't hear your name. Breda Chemtai, Breda McKenna, Choge, Daisy, Evans Marwa, Frida Karoki, Hope Onsongo, Jacinta Wajiko, then Joanne Abe, Joseph Camelo, Kananu, Kananu, is it Kananu? Esterine, Kimani Ann, Amek, Abenya, Lowin, Chemketich, Mugendi, James, Lydia Nadisa, Muide Nzao, Mwafwali, Naomi, it's quite a new name, Naomi, Sipatoi, Demo Patricia, Niala McKenna, Luanda, Christine, Omeni Oluoch, Shalina Kadeen, Sharon Mubua, Sylvia Irungu, Simon Waigwa, Sarah Joki, Tonui Vilea, Wedi Odwell. I'm having 35 of you. I have 29. Kindly chat me up if you didn't hear your name. I told you in 5th year. You're not. Mwenda Claire raised hand. Mwenda, you didn't hear your name? All right, let me write it. Sorry about that. Mwenda Claire, thank you. Another hand up, raised hands. Otieno, thank you. I just missed it out because some people kept signing in and out. So when they sign in and out, they change the arrangement. Those are 31. I have another 1, 2, 3, 4. I have 1, 2, 3, 4. Simon Waigwa, I have your name. Anybody else? I still have some more. About 4 of you who have signed in. Kiprop Eleka. Sorry about that. Eleka, another one who can raise their hands. I have another 3 who seem to be in class and have not been noted. 5, 6, 7, 8, 9, 10. 2 more. 3 more. Who else has not had their name? Who has not had their name? You need to, if you are there, you should be able to tell me. If you have just left your gadget and gone, of course, you're not hearing what I'm saying. So who else? Who else? Because I have 3 more names. Who else? Or there's somebody who has signed more than once. Anyway, kindly note, I said if you miss up to 3 lectures, we are now in 4th year. In 5th year, sorry. So hakuna mchezo. So if you miss your lectures, don't even bother. I will not allow you even to do the exam because you will only bring us problems. So I think with that, not unless if there's any other issue, let me save the names. Save us.